Welcome to Tech Girl Kannada YouTube channel.
Corrosion and Metal Finishing. Corrosion. Introduction. Electrochemical theory of corrosion. Factors affecting the rate of corrosion. Ratio of anodic to cathodic ratio. Areas. Nature of the metal. Nature of the corrosion product. Nature of the medium. pH, conductivity and temperature. Types of corrosion. Differential metal corrosion and differential aeration corrosion. Pitting and waterline. Corrosion control. Anodizing of aluminium. Cathodic protection. Sacrificial anode and impressed current methods. Metal coating, galvanizations. Metal finishing. Introduction. Technological importance. Electroplating. Introduction. Principles governing electroplasting. Polarization. Decomposition. Potential and overvoltage. Electroplating of chromium, hard and decorative. Electroless plating. Introduction. Electroless plating of nickel and copper. Distinction between electroplating and electroless plating process. Corrosion. What is corrosion? Definition. Corrosion is defined as the destruction of metals or alloys by surrounding environment through chemical or electrochemical reactions. When iron is exposed to air and moisture, hydrated ferric oxide rust is formed. 2Fe plus O2 plus 2H2O gives Fe2O3 dot H2O rust. Dry corrosion is due to the direct attack of dry air on metals through chemical reactions. Example, attack of dry air or oxygen on metals to form oxide layers. Wet corrosion takes place in conducting medium like water through electrochemical reaction. Example, rusting of iron. The rate of wet corrosion is faster than dry corrosion. Electrochemical theory of corrosion. According to electrochemical theory of corrosion, when a metal such as iron is exposed to air and moisture, the following changes occur. Formation of galvanic cells, development of anodic and cathodic areas results in formation of minute galvanic cells. At anodic area, metal atoms undergo oxidation to give metal ions. Fe gives Fe2 plus 2 electrons. At cathodic area, electrons released at anode flow to cathode and cause reduction reaction. Depending on the surrounding environment conditions, there are three possible ways of reduction reaction. If the medium is aqueous, aerated and neutral, oxygen reduced to OH minus. Half O2 plus H2O plus 2E minus gives 2OH minus. Aqueous, aerated and neutral. Aqueous means H2O will be there. Half O2, aerated means O2. Half O2 H2O plus 2E minus gives 2OH minus. If the medium is aqueous, deaerated and neutral, water reduced to H2 and OH minus. Here, 2H2O plus 2E minus gives H2 plus 2OH minus. If the medium is deaerated and acidic, H plus ion reduced to H2. 2H plus 2E minus gives H2. Metal ions formed at anode combine with OH minus ions to form metal hydroxide. Fe2 plus 2 OH minus gives FeOH twice. Metal ion formed at anode combine with OH minus ion to form the metal hydroxide. Finally, ferrous hydroxide reacts with oxygen and moisture to form hydrated ferric oxide, rust. 2 FeOH twice plus O2 plus N minus 2 H2O gives Fe2O3 dot NH2O. 2 FeOH twice plus O2 N minus 2 H2O gives Fe2O3 dot NH2O. Air, moisture, metal, raw. Anodic area, Fe gives Fe2 plus 2E minus. Cathodic area, O2 plus 2H2O plus 4E minus 4OH minus. Types of corrosion. Depending on how the anodic and cathodic sides develop on the surface of metal, there can be different types of corrosion. Differential metal corrosion. This type of corrosion is due to the contact of two different metals. Metal having low reduction potential acts as anodic, while metal having high reduction potential acts as cathodic. Differential aeration corrosion. This type of corrosion is due to difference in concentration of oxygen on the metal surface. Like area of metal in contact with less oxygen acts as anodic, while area in contact with more oxygen acts as cathodic. Stress on the metal. This type of corrosion is due to the stress on the metal. Area of metal under stress acts as anodic, while area under no stress acts as cathodic. Differential metal corrosion. When the two dissimilar metals are made to contact each other, metal having high reduction potential becomes cathode and the metal having low reduction potential acts as anode. Anode undergoes corrosion and cathode remains unaffected. The rate of corrosion mainly depends on the difference in electrode potential between the metals. Higher the potential, higher is the rate of corrosion. Potential difference, higher the potential difference, higher is the rate of corrosion. So use of two dissimilar metals should be avoided. In case if it is inevitable to use two dissimilar metals, select the metals in such a way that their potential difference should be very low. Example 1. Iron minus 0.44 volts in contact with zinc minus 0.76 volts. So iron is having more electrode potential. Higher the electrode potential, it acts as cathode. Since zinc has low reduction potential, it acts as anode, undergoes corrosion. Iron has high reduction potential, acts as cathode and remains unaffected. Example 2. Iron minus 0.44 volts in contact with copper 0.34 volts. Iron here Copper having the positive 0.34 volts. Positive reduction potential. Iron has low reduction potential compared to copper, acts as anode and undergoes corrosion. Copper has high reduction potential, acts as cathode and remains unaffected. Here at anode, Fe gives Fe2 plus Fe2E minus. At cathode, half O2H2O plus 2E minus gives 2H minus. Here then it becomes Fe2 plus OH2OH minus FeOH twice. FeOH twice O2 N minus 2H2O gives, it should be N minus 2H2O. 2 FeOH twice plus O2 N minus 2H2O. Differential aeration corrosion. This type of corrosion occurs due to the difference in concentration of air on the metal. Area of metal exposed to less air acts as anodic, and area of metal in contact with more air acts as cathodic. Corrosion begins at the point where anodic and cathodic sides meet. Metal partially immersed in the solution, which is exposed to the more aerated metal, undergoes reduction. Half O2 plus H2O plus 2E minus gives 2OH minus. And the metal part, which is in the less aerated space, undergoes corrosion by oxidation. Fe gives Fe2 plus 2E minus. When metal partially immersed in salt solution and metal part immersed in the solution acts as anode and undergoes corrosion. Waterline corrosion. More aerated, cathodic. Half O2 plus H2O plus 2E minus gives 2OH minus. Less aerated, Fe gives Fe2 plus 2E minus. Waterline corrosion is observed commonly in water tanks made of iron. Water filled part acts as anode and the metal part, which is uncovered with water, acts as cathode. Corrosion begins just above the waterline where both anode and cathode areas meet. Hence it is called waterline corrosion. At anode, Fe gives Fe2 plus 2E minus. At cathode, half O2 plus H2O plus 2E minus gives 2OH minus. Fe2 plus 2OH minus gives FeOH twice. At the reduction point, then again it goes oxidized. FeOH twice plus O2 plus N minus 2H2O gives Fe2O3 NH2O. Pitting corrosion. This is also an example of differential aeration corrosion. When dust particles get deposited on a metal surface, the region below the dust particle is exposed to less oxygen compared to the remaining part. As a result, the region below the dust particle acts as anode and undergoes corrosion and forms a pit. The remaining region of a metal acts as cathode, which means this is an example of differential aeration corrosion. When dust particles get deposited on the metal surface, the region below the dust particle is exposed to the less oxygen compared to the remaining part. As a result, the region below the dust particle acts as anode, undergoes corrosion and forms a pit. The remaining region of a metal acts as cathode. Cathodic area, dust, rust. Anodic area, pits. It forms a pit to store that dust. At anode, Fe gives Fe2 plus 2E minus. At cathode, half O2 plus H2O plus 2E minus gives 2OH minus. Fe2 plus 2OH minus gives FeOH twice. 2 FeOH twice O2 plus N minus 2H2O gives Fe2O3 NH2O. Factors affecting rate of corrosion. Corrosion depends on characteristics of metal surface and surrounding environment medium. Factors affecting the rate of corrosion. The factors related to the metals are primary factors and those related to the environment are secondary factors. They are listed below. Primary factors related to metal, anodic and cathodic areas, nature of corrosion product, electrode potential. These are related to the metal. Which are these? Anodic and cathodic area, nature of corrosion product, electrode potential. Secondary factor related to the nature of the medium, which is pH, temperature, conductance of the medium. Primary factors. The ratio of anodic and cathodic area. Smaller the anodic area, larger the cathodic area. Smaller the anodic area, larger the cathodic area. Corrosion process is more intense and faster. Because large cathodic area demands more electrons from the small anodic area. Due to this, oxidation occurs at faster rate, causing intense corrosion at the anode part. Example 1. Coating of tin on iron. If the layer of tin is broken or peels off, then the rate of corrosion is faster at the broken region. Because the exposed region of iron acts as anode with small area and tin acts as cathode which has larger area. On the other hand, if cathodic area is small, anodic area is large, the rate of corrosion is slower. Because coating of zinc on iron. If the layer of zinc is broken and or peels off, no intense corrosion is seen at the broken region. Because the exposed region of iron acts as cathode with small area and zinc acts as anode which has larger area. Example 1, intense corrosion. Example 2, slow corrosion. Example 1, intense corrosion, smaller anodic area, larger cathodic area. Slower corrosion, smaller cathodic area, larger anodic area. Nature of corrosion product. The corrosion product formed on the metal surface is their corresponding metal oxide. The characteristics of this metal oxide layer determines the rate of further corrosion. If the corrosion product is stoichiometric, highly insoluble, stable, non-porous, has low ionic and electrical conductivity, then it acts as protective film which prevents further corrosion. The film acts as barrier between the metal surface and the corrosive environment. Example, aluminium, titanium and chromium form a protective film of metal oxide on the surface and prevents corrosion. Metals such as Ta, Zr and Mo are not only form protective layers but also capable of self-repairing the oxide films. On the other hand, if the corrosion product is non-stoichiometric, soluble, unstable, has high ionic conductivity and porous, then the rate of further corrosion is faster. In the case of zinc and iron, the oxide layer increases the rate of further corrosion. Electrode potential. Electrode potential is the main cause for corrosion when two dissimilar metals are in contact with each other. If the potential difference between the two metals increases, the rate of corrosion also increases. Let us consider iron in contact with copper and tin. The potential difference between iron and tin is 0.3 volts, but the potential between iron and copper is 0.78. Hence, the rate of corrosion of iron is faster in contact with copper rather than in contact with tin. Here is another example. Electrode potential 0.44 for iron, and then strontium we have minus 0.14 volt. There is smaller difference at the corrosion between the iron and copper has larger difference. Secondary factors, nature of medium, pH of the medium. pH of the medium also decides the rate of corrosion because of the continuous evolution of H2 gas at cathode region. If the pH is greater than 10, the rate of corrosion is almost stopped due to the formation of protective coating of hydrous oxide layer. Hydrous oxides layer Fe2 plus 2OH minus gives FeOH twice. If the pH is between 4 and 10, the presence of oxygen is essential for corrosion. If the pH is between 4 and 10, the presence of oxygen is essential for corrosion. Half O2, H2O, 2E minus, 2OH minus. If the pH is less than 4, corrosion occurs severely, even in the absence of oxygen due to the continuous evolution of H2 gas. 2H plus 2E minus H2. Ship submerged in deep sea water remains almost unaffected, even hundreds of years, due to higher pH of sea water. Yes, ship submerged in deep sea water remains almost unaffected. Nice. Conducting medium. Rate of corrosion increases with increase in the conductance of the medium. As the conductance of the medium increases, charged particles can move easily through the medium. Therefore, the rate of wet corrosion is faster than dry corrosion. Temperature. Higher the temperature, higher is the rate of corrosion. As the temperature increases, conductance of the medium increases, hence the diffusion of the electrons from anode to cathode in general. The rate of chemical reaction, redox reaction, increases with increase in temperature. Therefore, the rate of corrosion increases as the temperature increases. Corrosion control. Corrosion is the electrochemical process. It can be controlled by preventing the redox reactions. The commonly used methods are protective coatings, metal coatings, anodic coatings, galvanizing, B, cathodic coating, tinning, surface conversion coatings, anodizing, phosphating, and chromating, organic coatings, painting, cathodic protection, sacrificial anode method, impressed voltage method. Metal coatings. Corrosion of metals can be controlled by isolating them from the surrounding environment. This can be done by depositing another metal on the surface of base metal. Coatings that are anodic to base metal are called anodic coating. Aluminium, magnesium, zinc, and cadmium are anodic to iron. These metals are above iron in galvanic series. Galvanizing. Coating of zinc on iron by hot dipping process is called galvanizing. It is an example of anodic metal conducting coating on iron. Pre-treated iron, organic solvent, rollers, dilute H2SO4, zinc chloride plus ammonium chloride, dryer, molten zinc at 450 degrees Celsius, excess zinc coated iron will be produced. Hot dipping method means there will be the pre-treated iron which is kept in the organic solvent along with the rollers in dilute H2SO4 sulfuric acid. Then it is combined with the zinc chloride and ammonium chloride and then dried. Then the molten zinc at 450 degrees Celsius is applied. It gets conjugated and then excess zinc has been kept. Then zinc coated iron will be obtained. Process galvanization involves the following steps. The iron sheet is subjected to the pre-treatment for the removal of organic impurities by treating with organic solvent. Inorganic impurities are removed by washing with dilute sulfuric acid. The sheet is then treated with a mixture of aqueous solution of zinc chloride and ammonium chloride. Ammonium chloride and zinc chloride acts as flux to prevent the trash formation by further oxidation of metal surface. Finally, the sheet is washed with water and air dried. The sheet is then dipped in the bath of bathe of molten zinc 450 degrees Celsius. The excess zinc on the surface is squeezed off, passing through a pair of hot rollers. Application: galvanization of iron is carried out to produce roofing sheets, fencing, wire, buckets, bolts, nuts, pipes, etc. Applications: galvanization of iron is carried out to produce roofing sheets, fencing wires, buckets, bolts, nuts, pipes, etc. etc. Anodizing. This is the process of interconversion of metal surface into a thin layer of its oxide. When aluminium metal is made anodic in electrolytic bath of sulfuric acid or chromic acid, a thin layer of aluminium oxide is formed on the surface. This process is called anodizing of aluminium. Process: aluminium is subjected to the pre-treatment to remove impurities and then made as anode. Electrolyte is chromic acid mixed with some quantity of sulfuric acid, maintained at about 35 degrees Celsius. Slowly increase the applied potential from 0 to 40 volts for first 10 minutes. Then increase it to 50 volts for another 5 minutes to get desired thickness of the oxide film. After the completion of anodizing process, it is treated with boiling water or steam and finally dyed with any suitable dye. Aluminium oxide layer formed on the surface of air acts as protective coating, hence corrosion is prevented. Aluminium oxides, anode aluminium, cathode stainless steel, anodizing of aluminium, mixtures of sulfuric acid, Cr2O3, chromic acid. Note: an anodizing aluminium oxide Al2O3 is formed on the surface as a porous layer. The layer may be made compact by sealing, which involves heating with boiling water or steam. During sealing, Al2O3 is converted into Al2O3.H2O, which occupies higher volume. Therefore, the pores are sealed. Applications: anodized aluminium finds lot of commercial applications, such as it is used in the making of escalators, roofing, staircases, ceilings, computer hardware, scientific instrument, etc. Cathodic protection. Corrosion of metal is due to the flow of electrons from anode to cathode regions. Anodic region undergoes corrosion and the cathodic region remains unaffected. The object of cathodic protection is to make the base metal cathodic by providing electrons to it, and from an external source. The external source may be any anodic metal to the base metal or external current. There are two methods: sacrificial anode method. In this method, the metal to be protected is electrically connected to more active metal. For example, when steel is to be protected, it may be connected to an anodic metal like magnesium and zinc. In such a situation, steel acts as cathode, remains unaffected. Magnesium or zinc acts as anode and undergoes corrosion. When the sacrificial anode gets exhausted, it is to be replaced with new one. Since the anode metal has to sacrifice its life to protect the life of cathode, it is called sacrificial anode method. In sacrificial anode method, the metal to be protected is electrically connected to more active metal. For example, when steel is to be protected, it may be connected to a block of magnesium or zinc. In such a situation, steel acts as cathode, remain unaffected. Magnesium and zinc acts as anode and undergo corrosion. When the sacrificial anode gets exhausted, it is replaced by new ones. Other examples, zinc strips were fixed to the sides of ships' hull to act as sacrificial anode. Zinc wire are connected to buried pipelines. Zinc wire are connected to buried oil storage tank. Impressed voltage method. In cathode protection, the metal to be protected is completely converted into a cathode. Since cathode do not undergo corrosion, metal is protected against corrosion. Impressed current method. Metal to be protected is connected to the negative terminal of external DC power supply. Positive terminal is connected to an inert electrode, such as graphite. Under these conditions, the metal acts as cathode, hence does not undergo corrosion. The inert electrode acts as anode, but it does not undergo corrosion because it is inert. Metal finishing. Definition of metal finishing. Metal finishing is a process of deposition of a thin layer of one metal on the surface of material by electrolysis method, metal, plastic, etc. Metal finishing is the process of surface modification of a metal. Electroplasting, electroless plating are the two important techniques of metal finishing. Technological importance of metal finishing. Metal finishing is carried out to obtain technologically important surface properties. These properties are a decorative appearance, offer corrosion resistance, impart thermal and resistance to impact, impart resistance to wear, tear, and abrasion, to provide electrical thermal conduction, offer the surface optical reflectivity. Technique is useful for the manufacture of electrical and electronic component PCB, capacitors and contact. Manufacture of metal articles and ornaments. Principles governing the electroplasting process. Polarization. Definition of polarization. Polarization is defined as a process where there is a variation of electrode potential due to inadequate supply of ionic species from the bulk of the solution to the electrode surface. Variation in concentration around the electrode. Consider an electrolytic cell under operation when current is being passed. Positive ions are produced at the anode and are consumed at the cathode. If the diffusion of ions in the electrolyte is slow, there will be accumulation of positive charged ions in the vicinity of anode. Similarly, there will be a depletion of ions in the vicinity of cathode. Under these conditions, the anode and the cathode are said to be polarized. This type of polarization is called concentration polarization. Accumulation of products around an electrode. Products of electrolysis at the electrode set up additional active electrodes whose potential opposes the applied EMF. Example, during electrolysis of water, using smooth platinum electrodes H2 and O2 are active electrodes. Platinum H2H plus platinum O2H minus produce back EMF in opposite direction.
to the applied EMF, altering the output potential. In galvanic cells, polarization leads to variation of electrode potential. Electrolytic cell polarization leads to use of higher potential than required theoretically. Factors affecting the electrode polarization. Nature and size of electrode. Electrode with rough and large surface have low polarization. Nature of products formed by the electrode. If the products of form or film on the surface, polarization increases. Name of the nature of the electrolyte. Lower the concentration of the electrolyte, lower is the polarization, but it should be more conducting. Temperature. Higher the temperature, lower is the polarization, because at high temperatures the rate of diffusion of ions is very higher. A rate of stirring of the electrolyte. Stirring helps in minimizing the polarization effects. Definition of decomposition metal. Decomposition potential is defined as the minimum external potential required for the continuous electrolysis of electrolyte. Electrolysis of an electrolyte occurs only when applied voltage is above certain value, below which the electrolysis did not occur. This can be determined by an electrolytic cell. If dilute acid or bases are used as electrolytes, it required more than 1.7 volts. Determination of decomposition potential. The decomposition potential is determined using an electrolytic cell as shown in the figure. The cell consists of two platinum electrodes immersed in the dilute solution of an acid or a base. The voltage is varied along with the wire, and the current passing through the cell is measured using an ammeter. At low voltage, no reaction occurs, and there is a very slight increase in the current, and small amount of hydrogen and oxygen are liberated at the cathode and anode respectively. This hydrogen gas absorbed on the cathode electrode and produces back EMF, which opposes the applied EMF. On increasing the voltage to slightly above 1.7 volts, there is an abrupt increase in current, and process of electrolysis begins. A plot of the current against the applied voltage as below. Significance of decomposition potential. Minimum external voltage can be determined for the electrolysis of electrolyte. It is impossible to predict the order of discharge of ions from an electrolytic solution containing several ions. Definition of overvoltage. Overpotential. Overpotential is defined as the excess voltage that has been applied above theoretical decomposition potential to start the electrolysis. Decomposition potential determined by above method. New. Experimental decomposition potential minus theoretical decomposition potential. Nu is equals to E exponential minus E theor. Example. For electrolysis of water using smooth platinum electrodes, the theoretical decomposition is 1.3, experimental decomposition potential is 1.7. The difference is 0.47 volt. This is the over voltage. Factors affecting the over voltage value. Nature of the electrode. Electrode with the rough surface have low over voltage. Nature of the product produced at the electrode. If the products form electroplasting. Definition. Electroplating is a process of electrolytic deposition of a metal on the surface of another metal substrate. The substrate may be another metal, a polymer, a ceramic, a composite. Electroplating of chromium, decorative chromium and hard chromium. There are two types of chromium coating: decorative chromium plating, thin deposit of 0.25 to 0.75 micrometer, applied over copper nickel or nickel undercoat to give pleasing look and non-tarnishing nature to the plated article and industrial of engineering. Chromium directly on the substrate thickness 2.5 to 300 micrometer. The surface of the object is cleaned thoroughly. Organic substances are removed by the solvent cleaning and alkali cleaning. Inorganic substances are removed by mechanical cleaning and pickling. Finally, the surface is washed with deionized water. Then, chromium plating is done under the following conditions. Chromium plating, decorative chromium. Anode insoluble anodes like PBSN or PBSB coated with PbO2. Cathode object to be plated. Bath composition 100 is to 1. Chromic acid and H2SO4. Current density 100 to 200 milliampere per centimeter square. Temperature 45 degree to 60 degree. Current efficiency 10 to 15%. Application provides durable, good finish on automobiles, surgical instruments. CrO3 plus H2O, H2 CrO4, CrO4 2 minus 2H plus. 2H2 CrO4, H2 Cr2O7 plus H2O. H2 Cr2O7 Cr2O7 2 minus plus 2H plus Cr2O7 2 minus plus 14H plus 6E minus catalyst sulfuric acid 2 Cr3 plus 7H2O Cr3 plus 3E minus Cr Cr2 Cr3 plus 3O2 PbO2 gives 2 CrO3 plus 6 electrons. In chromic acid, chromium is present in 6 plus oxidation state. It is first reduced to 3 plus state by a complex anodic reaction in the presence of sulfate ions. The Cr3 plus then gets reduced to Cr on the substrate surface for a good deposit, and the Cr3 plus concentration must be low. The PbO2 oxidizes a part of Cr3 plus to Cr6 plus, thus reducing the concentration of Cr3 plus. In chromium plating, we do not use chromium metal as anode due to the following reasons. If chromium dissolves at anode, there will be a high concentration of Cr3 plus in solution. In such cases, a black deposit is obtained. In acidic solutions, chromium may undergo passivation. Electroless plating. Definition of electroless plating. Electroless plating is the process of depositing a metal from its salt solution over catalytically active surface by controlled chemical reduction by a suitable reducing agent without using electrical energy. Principal components composition of an electroless plating bath. An electroless plating bath contains the following components: source of electroactive metal in the form of soluble salt NiCl2CuSO4, reducing agent to reduce metal ions into metal atoms. Example: sodium hypophosphate, formaldehyde, sodium borohydride, hydrazine. Complexing agents to form complex compounds with metal ions. Example: citric acid, tartrates, EDTA. Exaltant accelerator to increase the rate of plating. Example: succinate, glycinate, fluorides. Stabilizer to give more stability to solution. Example Theoria, Ca, calcium, Pb, thallium. Addition agents such as brighteners. Buffer to control pH. Electroless plating of Ni. Before electroless plating, the surface is thoroughly cleaned. Then electroless plating is done under the following conditions. Plating bath solution NaCl2 20 to 30 gram of L. Reducing agent sodium hypophosphate NaH2PO2 20 gram per liter. Complexing agent and exaltant sodium cyanate 15 gram bar L and saccharin coumarin. Buffer pH 4 minus 4.5. Boric acid 30 to 45 gram per liter. Sodium acetate 10 gram per liter. Temperature 90 degrees Celsius. Anode reaction H2PO2 minus H2O H2PO3 minus 2H plus 2E minus. Anode reaction Ni2 plus 2E minus gives Ni. Overall reaction H2PO2 minus H2O Ni2 plus H2PO3 minus 2H plus Ni. Since H plus ions are produced during the reaction, the pH decreases. To maintain the pH at 4.5, buffer salt, boric acid, and sodium acetate is added during the reaction. Thick nickel coating exhibit very good corrosion, wear, and impact resistance. It can be coated on steel, zinc, copper, and its alloys. Applications used to obtain a wear resistant surface and decorative enhancement as well as protection of components from the corrosion. Ni coating on aluminum improves the solderability. Ni coating on polymers is used to obtain decorative knobs in hi-fi equipment, tops on bottles, etc. Electroless plating of copper. Before electroless plating, the surface is cleaned thoroughly. Insulators such as plastics and printed circuit boards are activated by dipping first in stannous chloride SnCl2 and then in palladium chloride PdCl2. Then the electroless plating is done under the following conditions. Coating solution CuSO4 solution 12 gram per liter. Reducing agent formaldehyde 37% solution 170 milliliter per dm cube. Buffer NaOH 15 gram per liter. Rochelle salt 14 gram per liter. Complexing agent exaltant EDTA 20 gram per liter. pH 11. Temperature 25 degree Celsius. Anode reaction 2HCHO plus 4OH minus 2HCOO minus plus 2H2O H2 plus 2E minus. Cathode reaction Cu2 plus 2E minus Cu. Overall reaction Cu2 plus 2HCHO plus 4OH minus Cu plus 2HCOO minus plus 2H2O plus H2. Formaldehyde and copper sulfate are added to the plating bath periodically. Application melting, use it for metallizing printed circuit boards, use it to produce through hole connection. through-hole connection in PCBs application. For PCBs with double-sided circuits, through-hole connection is required. The through-hole connection is made by electroless plating technique. To start with, this two sides of plastic board is electroplated with copper. Selected areas are protected and the remaining areas are etched away. Thus, two circuits are produced on two sides. The connection between two sides is made by drilling hole followed by plating through holes by electroless plating. The various steps are shown in the figure. Copper foil, insulating base, copper foil, etching of copper to produce tracking, drilling of through holes, activation of surface, then electroless plating of copper, copper electroless to build up deposit thickness. Differences between the electroplating and electroless plating. Difference. Property: driving force. Electroplating power supply, electroless plating autocatalytic redox reaction. Anode reaction: Mn plus Ne minus or H2O gas half O2 plus 2H plus 2 electrons. Reducing agent gives oxidized product plus Ne minus. Cathodic reaction: Mn plus Ne minus gives M. Here also Mn plus Ne minus gives M. Site of anode reaction: separate anode in electroplating. Article to be plated is the electroless plating site of anode reaction. Site of cathode reaction: article to be plated is the cathode reaction site. Here article to be plated with the catalytic surface is the cathode reaction site. Anode reactant: M or H2O. Reducing agent: nature of deposit: pure metal or definite alloy. Usually metal contaminated with reducing agent, the rare species. That's it. Thank you for watching. Do like, share and subscribe to my channel.